All right, good evening, everyone. My name is Dustin Lowe. I'm a junior chemistry major at Coastal Carolina University, and I'm here today to present to you on glycogen storage disease type 3, also known as Cory's disease, a term which I will be using interchangeably throughout this presentation. All right, so a little about Cory's disease. It was discovered and classified back in the 40s by its namesakes, Carl and Gertie Cory, who won the Nobel Prize for this discovery. We currently know of 4 types of Cory's disease represented by A through D. Now, A and C affect only the tissue in the liver, whereas B and D affect the musculoskeletal tissue as well as the liver tissue. Individuals with Cory's disease experience a deficiency in the enzyme used to break down glycogens in those tissues, resulting in a buildup of partially broken down glycogen pooling in the body. So Cory's disease is not an infectious disease. It's not a virus. It's not a bacteria. It is a genetic disease. Cory's is inherited in what's referred to as an autosomal recessive pattern, as according to my diagram here. This means both parents must be carriers of this disease in order for the offspring to inherit it. It's not entirely common, as it only occurs around 1 in every 100,000 births. Even with both parents being carriers, it only occurs in around 1 in 4 of their offspring. Cory's is caused by a genetic mutation in something called the AGL gene. Now, the AGL gene is responsible for the production of the glycogen debranching enzyme. This gene is 82 kilobase pairs in length and is located in the first chromosome in the band 1p21.2. Most mutations in this gene result in inactive versions of the glycogen debranching enzyme, while some result in enzymes working in a reduced capacity. But what are glycogen debranching enzymes? So Cory's disease is defined as a deficiency in an enzyme called the glycogen debranching enzyme. Since the body needs energy, and having an abundance of loose glucose in the body is just terribly inefficient, the body stores its glucose in globules called glycogens. I'll get to those in a moment. In order for the body to fully take advantage of its glucose reserves, it has to be in a linear state. Now, GDE works in conjunction with phosphorylase for that. The phosphorylase digests the linear glucose down to a length of about 4 residues from the branch point, as you can see by the pink glucose on my chart here. However, the phosphorylase can only cleave the alpha-1,4 glycosidic bonds, shown here in blue. Glucose has been seen to branch off the linear chain to form new alpha-1,6 glycosidic bonds, as you can see here in pink. Without the debranching enzyme, the phosphorylase would only be able to digest down to the branch, but then it would have to stop. With the addition of the debranching enzyme, metabolism can continue with only a minor setback. So a little bit of an explanation on the graphic. This perfectly represents the breakdown of glycogen in metabolic processes. The phosphorylase breaks down the glucose chain until it gets to 4 residues from the branch, as we've talked about. A transferase comes in and moves all but the branch glucose to the end of the linear chain. Finally, the branch glycogen is released through a hydrolysis reaction to become a free glucose, and metabolism continues. So being able to process glycogens in your body is pretty important. Now, since we've established that glycogen is important, how important is it really? Glycogen serves as the body's main source of energy. Animals, fungi, some bacteria. In humans, glycogen is made and stored in the liver and the musculoskeletal tissue. In terms of mass, your liver is about 5 to 6% glycogen. It's a pretty significant presence. Structurally, glycogen is very similar to the starch that serves as the energy in plants. If you've ever had a potato, and really who hasn't, they're mostly starch, and those are not too friendly to your body. And speaking of the body, since we've covered what causes this disease and how that differs from a healthy individual, let's talk about how this deficiency affects the body. Symptoms of Cory's start in early infancy, manifesting as things such as low blood sugar, also known as hypoglycemia, and elevated levels of liver enzymes in the blood, as well as a condition called hyperlipidemia, where the blood has a high level of fats. Now, as the patients age, they typically experience an enlarged liver, also known as hepatomegaly. At adolescence, though, liver size usually returns to normal, but some individuals will develop cirrhosis as a result, leading to liver failure later in life. These liver problems often lead to affected individuals having a shorter stature than normal, In simple terms, your body can't process the energy it needs to grow to its full potential while you're young. Later in life, these individuals typically develop muscular weakness, also known as myopathy, affecting both the heart and skeletal muscles. Fortunately, though, even though the heart is weakened as a result of quarries, heart failure is a rarity. But since we talk about all these symptoms, let's talk about what we can do to help these people. Currently, we have no definitive cure for quarries. However, a few treatments for individual symptoms have risen to prevalence. Some treatments are relatively simple. For example, hypoglycemia can be somewhat regulated by more careful dieting. Unfortunately, not a whole lot of treatments can exist for cirrhosis, save for a liver transplant. Some pharmacology-based treatments exist for times of cardiac trouble as well as extreme pain. Also, if we as a society can overcome the moral ambiguity associated with CRISPR, then it's incredibly likely we will find a cure down that road as well. Alrighty, thank you all for listening.